I'm really excited to show you some big insights I just learned about NVIDIA. Most investors think NVIDIA builds chips for AI training, but I'm going to give you an exclusive look at a very different side of the story. I'm joined by Dion Harris, NVIDIA's Senior Director of High Performance Computing, Cloud, and AI Infrastructure Go-to-Market. Dion has been with NVIDIA for 9 years, deploying the hardware and software infrastructure powering some of the biggest AI models on the planet, not just for training, but also for inference. I asked Dion as many in-depth questions as I could, and he had a few surprising things to say about where the AI market could be headed next. Your time is valuable, so let's get right into it. I'm going to jump right into the hard questions if you don't mind. When I think about NVIDIA, I think NVIDIA is really widely known for its leadership in AI training. But for investors who are newer to AI, could you kind of explain how NVIDIA's GPUs and their infrastructure at large support all the phases of AI?
Yeah, so that's a very, very sort of key observation is like when AI really first popped on the scene, there was really a race to create, the sort of most capable foundational models, right? And so that's where you had models like ChatGPT, you had Claude, you had a number of other foundational models that were really being built and trained at scale. And so training is exactly like it sounds. It's teaching the model foundational knowledge about the world. That's where you hear models being trained on the entire content of the internet, for example. And it's really just helping the models learn and understand, semantic language, learn and understand different meanings across different modalities. And so that's really foundational knowledge. And then the next part of providing intelligence is what we call post-training. And so that's once you've taken a foundational model that has very base foundational knowledge, so just like the name describes, but then you inject additional specialized knowledge. So it might be post-training a foundational model to understand your particular industry. For example, healthcare has very specific terminology, very specific uses of certain words. So when you say cell in healthcare, it means something different than when you say cell in the legal profession, for example. So understanding the nuances of a specific industry or a specific company, that's really where you're injecting more specialized intelligence within your post-training phase. And then inference is really where you put AI to use. In other words, you've trained a model, you've fine-tuned a model, and now you want to actually use it with end users, with customers, with partners, and really deploy and extract the value out of AI. And so that's really where we are right now in terms of all the investment in AI infrastructure. A lot of it in the early days was to build training clusters. Now that AI has reached sort of a critical tipping point in terms of intelligence and utility, we're seeing it deployed for inference at scale.
And I think the real big insight you just said there is it's not even just two steps, right? It's not just training and inference. The post-training step is incredibly important as well. I've been diving deep into AI for a while now, and one thing I've realized is that inference is more than one step as well. So it's not just training, post-training, and inference. For example, there's prefill and decode, each of which have very different computing requirements. Can you sort of explain what these phases are, how NVIDIA addresses each one individually?
Yeah, sure. So like you described, inference itself can be decoupled into a couple of different workloads. There's prefill, which is really where you're taking the context of the query. You're processing and understanding what the user wants. So it might be just the question or the prompt they enter. It might be the document that they upload so that you can draw upon that document as source information to build a response. Or it may be previous responses that the user has generated or created over the life of engaging with that model. So the prefill is really about understanding the context for the question or for the prompt being asked. Once it does that, it can generate a single token. And then you can move into the decode phase. The decode phase is actually doing the autoregressive prediction of each token that comes as a result of the AI generation model. And so the reason why that's really interesting is when you think about those specific workloads, they have slightly different infrastructure requirements, if you will. So when you think about the prefill or the context heavy, it's really compute heavy. It's really focused at understanding all the different tokens that are being put into the system to formulate contextual awareness. However, when you look at decode, it's much more memory latency bound. And so it gives a lot more credence to having things like HBM or high bandwidth memory to really generate those tokens very quickly. Now, the other thing they really think about is there's no one size fits all, right? Each model, each user profile might have a different balance or mix of prefill and decode. And so that's part of what makes inference particularly challenging, is that you don't have a sort of prescriptive way of understanding exactly what that mix should be, because it's going to vary depending on users, depending on the type of request that they're asking. So, for example, if they're doing a deep research project, it's going to be a lot more prefill heavy than decode, because you need to go through and sift through all those PDFs that you might upload to go and understand all the contextual information. However, if you're going to ask the AI to produce a long, in-depth code base, it might be more decode heavy, because it really needs to understand, just all the interdependencies and run through lots of reasoning chains to create high quality code. So again, it's going to vary depending on the use case and the actual user, sort of the user objective and intention.
Yeah, so let me make sure I understand this just for myself too. So prefill is really about understanding all of the context in it once, right? So all the PDFs I upload, if I have a very detailed prompt, if I give a AI tons and tons of links, so the bigger the context window and the more I fill that up, the more compute intensive the prefill step is, as opposed to the decode, which is more about, understanding the tokens in sequence, adding the next token, then reanalyzing that whole sequence to add the next token, which is very different from understanding all the data at once. Is that like a fair high level overview?
Great summary. So I appreciate that. Yes, you always do a great job of taking my long-winded examples and making them very, very understandable and distilled. So I appreciate that.
No. And sorry, I want to just make sure like we're really clear about what we're talking about, because, with those very different compute requirements comes the need for very different hardware, right? So I know that NVIDIA recently announced the Rubin CPX GPU, which is a GPU specifically for the prefill step. So can you tell us a little bit about the CPX?
When we think about CPX, it's really purpose-built for what we call the million context workloads. So that's for things like advanced code generation, right? Where you have lots of data that you need to input. You might have an entire application code base. And if you want to understand all the interdependencies, how they actually deliver, sort of the end-to-end optimization, you would want to understand the full million tokens when you're generating the prompt or generating the code. There's also things like video generation, right? Where you need to have contextual consistency and awareness. So if you have a 2-hour video, if you have a million tokens, you can make sure that as you move throughout the scenes, you can, keep the scene integrity and make sure the characters have consistency and different elements of the story play through, because you have this large context window. So again, these are just some cutting edge use cases that we're starting to see that will rely on what we call the million context workload.
Yeah, so what I'm really taking away from this is prefill is very compute intensive, but not very memory intensive. So the CPX, the goal of the CPX is to provide all that compute, but lower the cost of the memory, since you don't need it at that step yet anyway. So then my next question is, will we see a separate chip with the opposite specs for the decode phase, right? Something that's very memory heavy, but compute light?
So what I would say is, when you look at sort of how we've designed our Rubin platform, most, I would say 80% of the workloads will do great on a classic Vera Rubin platform. But we think for these large, or what we call extreme massive context workloads, like I mentioned, like some of the code generation, video generation, and others, those are ones where you want to actually specialize, where you can really get some significant bang for the buck by actually having a specific prefill built processor.
Got it. So Rubin is already great at decode, and it was the prefill step that needed a separate phase optimized chip, for lack of a better word.
Exactly.
That's awesome. That really helps me understand the whole ecosystem. And I guess that's a really good lead in to another question I had. When most investors think about AI, they think about AI performance really being driven by the GPU, right? So when we're talking about the Rubin versus the Rubin CPX, we're talking about prefill and decode being driven by primarily these two GPUs, right? But, Jensen just gave a great keynote at GTC DC, and he talked about how NVIDIA co-designs at least 5 other chips every generation, right? A CPU, a DPU, NVLink. Can you help explain how all these other chips fit together?
Yeah, no, and that's a great question, because when you look at sort of the generational leaps that we're describing in a lot of our platforms, you can't get there just by adding more transistors to a single processor. Moore's law, Amdahl's law has sort of tapered out decades ago, and so we recognize in order to create these sort of massive leaps in performance, it requires what we call extreme co-design. And that involves not just looking at the GPU itself, but like you mentioned, the CPU, making sure that you have tightly coupled access to memory and processing power across the CPU and GPU. It actually leverages the blue filter, the data processing unit, as you're moving information, not just within the GPUs, but moving it to and from storage or getting access to the node itself. So having integrations with the software to make sure it takes advantage of not just the CPU and GPU, but also the DPU. And then, of course, when we think about what's happening with the scale of AI, it's no longer fitting into a single GPU or even a single node. So the scale up architecture is critically important now. In other words, being able to have several GPUs, CPUs, and processors behave as one. And so that's where our NVLink switch technology comes in. We build a specific chip around the switching technology that allows for seamless scale up. And then, of course, it's not just scale up, you have to be able to scale out. And so we've developed our Spectrum X Ethernet switching technology to scale out, to hundreds of thousands and millions of GPUs. And then we also have our InfiniBand network that also allows you to scale out. So again, it's really just depending on how customers choose to scale, but giving both options is really core to our platform. And I think when you look at all of these elements together, that's really the core of how we think about building systems, not just on a single chip, but looking at the full system to compute to networking. And then on top of that, you also have to think about how do you integrate with the models? How do you, work with the open source community to get them to build models and software that takes advantage of all the underlying hardware? So I'll give an example. We released Blackwell with a precision called NVFP4. NVFP4 is useless unless you teach the software to understand, how to use that lower precision smartly or intelligently. And so a lot of the work that we do in terms of this extreme co-design doesn't just stop at the hardware layer. It actually reaches into the model developers and builders to make sure that we're helping them leverage all of the different hardware innovations that we're making available through our architecture. So like I said, there's co-design happening at the CPU, the GPU, the DPU, the networking scale up, as well as the networking scale out, in addition to the models and applications themselves. And that's why we've described this as an annual rhythm. And that is sort of, for two key reasons. Models are evolving so quickly. Therefore, we have to evolve our platform just as quickly to make sure that we're keeping pace and unlocking sort of the next wave of use cases. So, for example, like I said, we talked about Blackwell last year, and we've already announced Blackwell Ultra. And of course, we've rolled out Vera Rubin, and we've already rolled out Vera Rubin CPX. And so, again, it's really that sort of yearly cadence that gives us the ability to keep leapfrogging ourselves and providing more performance and more value. So that's really the core sort of focus of our strategy and how we want to deliver this to the market.
It's an insane pace, and it's so cool to see the evolution of the hardware year after year after year. I'm really excited for next March when I hopefully get to touch the Rubin chips for the first time, and see like the Rubin version of the stack we've been going through ever since Hopper. So, you're describing some massive technical wins here. But as an investor, I think what we all really want to understand is how AI relates to real businesses, right? So can we take a step back and talk about why businesses should care about these kinds of inference speeds and compute efficiencies we've been talking about this whole time?
Inference is how you extract the value from AI. In other words, building a model doesn't create value unless you can use it and apply it to solve business problems, right? And so inference is really where the rubber hits the road in terms of getting AI to solve a business problem. And so once you take a step back and say, okay, if you're leveraging AI to go and solve a business problem, and if you're doing that at scale, this is what we call an AI factory. And so, going back to, the turn of the century, the factories were about, putting raw materials in and getting some finished product out. Today, when we say AI factories, it's about putting energy and electricity in and systems and components in and getting intelligence out. And so when we describe some of these performance improvements, think of it as, how much more intelligence can I produce per dollar or per watt? And once you think about it in those terms, you really quickly begin to see that efficiency is really the biggest driver on how you're going to get a return on your AI investment. So to the extent that you can improve your overall inference, your performance per watt, for example, if you're a power limited data center, which most data centers are today, you're trying to think, okay, how can I get more intelligence out of that power envelope? And so a lot of these sort of improvements that we describe, where we're describing the X factors, these translate into actual dollars and cents in terms of how many more tokens can be generated and therefore how much value can be extracted out of that AI factory. And if you happen to be an AI factory that's producing tokens and receiving money for tokens, it is a direct correlation in terms of how much throughput can you generate for a given power envelope or a given sort of investment value. And that has a direct correlation with how much revenue and therefore profit you can generate from that AI factory.
That's really interesting. So we should see that come up in companies' revenues and profit margins as they start leveraging more and more AI for more and more use cases as the cost comes down. But profits and margins are really something you see in the rear view mirror, right? So one of the questions I have is I try to look at forward looking indicators as an investor. What benchmarks or metrics can we focus on to better understand the real business value for inference in real time?
As you drive more performance, more throughput per dollar or per watt, that actually reduces the cost per token. And when you reduce the cost per token, you can actually embed that AI into even more services, even more use cases, and therefore deliver more value to your end users. When you think about AI, it's a lot more than LLMs. So it includes image classification, it includes video generation or diffusion models, it includes lots of different types of recommender systems that are being used to serve ads and content. And so when you think about today where we are, we're in a fairly demand driven economy, means there's a huge demand for a lot of these AI capabilities, but again, you have to be able to do it intelligently and smartly. If you can drive the cost down to zero, now you can literally embed these AI APIs into every application that you're running. And therefore, that's when you really start to see this ubiquitous use of AI. And so that's really why when we think about how we want to drive more performance and more efficiency, the cost per token going down by 10x will actually increase the overall utilization by 20x. Because now you have a lot more use cases where you can afford to embed these AI capabilities.
Yeah, right. For every dollar the cost goes down, the demand goes up by more than that same amount, right? Because
Exactly.
Maybe use cases that couldn't afford it at all can now jump in, and so you're increasing the whole surface area of AI overall.
I think that's a really important point to understand about inference. Is there's a lot of levers, there's a lot of complexity, and so it really is in some ways harder than training. I think oftentimes people assume that NVIDIA has an advantage because we've been doing training for so long, but we think our true advantage lies in our ecosystem and our software maturity that really was going to really go and tackle inference and make our platform even more valuable in inference than it is in training in a lot of ways.
Yeah, and I mean, just sort of 2 points there, right? One, inference means something very different than it did 3 years ago when ChatGPT first came out, right? One shot back then versus reasoning today. Now inference is a much more compute intensive workload. And two, something that we hear Jensen say all the time is inference and training are actually going to one day be one process, not two separate processes. What do you think about that statement?
I think it's a pretty fair statement, and I would even correct it a little bit. I would think that one day is actually today. And in fact, when you look at how most reasoning models, and you hit on this earlier, the way that you create a reasoning model, you train it with lots of inference. And it's giving you this iterative feedback loop by giving it and teaching it how to reason and rationalizing by leveraging inference outputs and then feeding that back in, that backprop that happens during training. So it really does leverage inference while you're delivering the training capabilities as well. So those workloads or processes are already starting to merge to the point where they're indistinguishable, quite frankly.
I find it so crazy how fast AI is moving. Jensen was on a recent podcast where he said that the demand for inference will rise by more than a billion X over the next few years. So, we talked a lot about NVIDIA's platforms today, but what is NVIDIA doing to keep up with the insane growth in demand? Like, how can we expect NVIDIA to keep up with next year and the year after that and the year after that?
Well, I mean, if I had to put it into, two words, it would be extreme co-design. And the one thing I just wanted to highlight is, when you describe the benefits of this extreme co-design approach, the fact that we demonstrated the inference max results, we demonstrated a 10x per watt over our previous gen Hopper platform. So 10x Blackwell versus Hopper in one generation. There's no way you can get 10x out of just delivering more transistors in a GPU. It really took the entire extreme co-design approach in terms of leveraging scale up NVL72, which allowed us to do lots of different parallelization techniques. It also created an opportunity for us to leverage our Dynamo software by leveraging disaggregated serving, and then of course the more transistors and the better perf of our NVFP4, while also maintaining the accuracy within the inference model. So all of these things together is what translated into that 10x delivered performance. And so, just highlighting that is really sort of unthinkable. Like you never would have thought of getting 10x in a generation over generation sort of improvement. But this is really what this approach brings. And like I said, we're not focusing on that single GPU. We're looking at the entire system, and now we're looking at the entire infrastructure, supply chain, and pipeline to drive even more efficiency. So just a case in point, but I thought that was a key point to highlight.
No, I think that makes a lot of sense. What I'm really hearing you say is NVIDIA doesn't just rely on Moore's law, right? Like chips aren't just getting whatever it is now 1.5 times better. Let's just call it 2 times better every 2 years. It's really about optimizing across the whole stack. And when you take a step back and do that, not even at the tray level or even the rack level, but the data center level, and you focus on everything all at once, which is why you guys co-designed so many chips, that's how you achieve 10x performance every year as opposed to 2x performance every 2.
Absolutely.
Makes a ton of sense, and it really puts, I think, the whole conversation in one unified context, right? Like, how do we drive performance at the whole data center scale?
And then what makes it even more complex is, as if that isn't hard enough, we then take it and say, how can you disaggregate it completely? How can you run our GPUs with another networking? How can you take your GPUs and include it with our new NVLink Fusion, which allows you to use our scale-up architecture? So we're not only making this fully integrated co-design stack, we're also making it, sort of modular enough and disaggregated enough such that we can, plug in wherever the user is. And so to make sure that we can build a solution that's right for them, even though we deliver what speed of light in terms of the full stack, but we want to recognize that every user is different and every user has different business objectives. And so, as if it wasn't hard enough to build a fully integrated stack, we're also building it, disaggregated so it can be consumed in so many different ways. So that's just another layer of complexity that we're kind of imposing on ourselves, because it makes perfect sense from a data center builder's perspective. They're already deploying NVL72 scale-up architecture for the majority of their data center. Why not look at standardizing as a way to scale up and scale out their architecture? So it's a lot of excitement, but again, I think it's just another dimension by which we're trying to create value, is not just giving you exactly what we build, but giving you the pieces that actually add value for your deployments. In fact, at GTC, we announced something called DSX, which is basically it's a mixture of digital twin capabilities along with gigascale AI factory reference blueprints that helps the entire ecosystem build to a common design of figuring out how do we build that gigawatt scale AI factory, but as efficiently as possible by leveraging a lot of our core best practices, as well as building within the digital environment, the digital twins, to really make sure we can build, operate, and design these systems much more effectively. So all of that is going to really power the next wave of AI, quite frankly.
The way everything fits together, both the co-designed chips, then how that scales up to the data center level and even across multiple data centers, then all the software and control systems that sit on top of it. Is there any one thing out of everything we've talked about so far that really excites you the most as you look to the future?
Well, I think it's really this notion that we are working across as a collective, right? We are literally working across every partner ecosystem, every developer ecosystem to bring sort of these solutions together that will hopefully power the next wave of AI. And so NVIDIA recognizing we can't do it by ourselves. And that's why we've always had this sort of approach of developer first. You know, from the very early days of accelerated computing becoming a new programming model, it resided in identifying applications and developers that could extract the value out of that platform. So we take that same approach today as we look at the next wave of AI. How do we create the conditions, you know, with new processors like CPX? How do we create the conditions with new software like Dynamo or new, you know, sort of architectures that can, you know, unlock a whole new set of use cases for all of the developers? And so once we look at that, you know, through all the customers we're talking to, all the feedback we're getting, it's really exciting to see how the light bulbs are going off in their heads thinking, what would I be able to do if I could have these different capabilities? And so as we sort of, you know, position our products and platforms, it's really exciting to see how the light bulbs are going off in the developers community heads of how they're going to leverage that to build things that we haven't even thought of yet. So pretty exciting stuff. Like you said, tiring because it's a relentless pace. But, you know, again, this is definitely exciting times. And I think NVIDIA is honored to be kind of at the epicenter of this whole incredible transformation.
And you know what I've really learned and taken away from this conversation is, you know, when we think about AI and NVIDIA, it's more than just about training, right? There's so much compute and there's so much consideration that goes into the inference side of things that NVIDIA has to build specialized chips for inference, co-design many chips to make inference work at large scales. I have a whole new appreciation for everything that NVIDIA does across the entire stack when it comes to inference specifically. So I can't thank you enough for your time, Dion. I'm super excited about what's to come, and thank you very much. A huge thank you to Dion Harris for walking us through NVIDIA's hardware ecosystem and how it powers every phase of AI, from pre and post training to prefill and decode for inference, and not just for large language models, but for everything from image and video generation to recommender systems, robotics, and beyond. And of course, thank you for watching and supporting the channel. Until next time, this is ticker symbol U. My name is Alex, reminding you that the best investment you can make is in you.